Here, and this is my Lab 1 constant velocity for Physics 2211. First off, we use Newton's second law to describe the motion of an object. In this lab, we took a video of an object moving at a constant velocity and analyzed the video to find out its position versus time graph. We then made a computational model based on the average velocity, and our goal was to compare the observed and computational models and draw conclusions based on physics principles. Some key physics principles in this lab is that the system is the basketball, the surroundings are everything other than the basketball, the interactions are the push on the ball, and constant velocity, which is an object moving with a constant magnitude and in a constant direction with a net force equal to 0. Some relevant equations are the position update formula, the velocity update formula, and Newton's second law, F net equals ma, which can derive the two above. Below is a picture of my calculations, which show an initial and final position and time, which then allow me to calculate the average velocity here, which I will use in my computational model later. I used the third and first position because it was an accurate time that allowed me to get a representative average velocity that will give me an accurate graph. Here are two force diagrams. The first is the force diagram when I'm pushing the ball and speeding up. As you can see that the net force is not equal to 0 and thus has an acceleration. And here is the force diagram when it is in constant velocity. The net force is 0 because the normal force and force due to gravity cancel out. Some key assumptions that the net force is equal to 0, there's no friction, and there's no air resistance. So continuing on to my tracker, you can see that I set the origin at the center of the ball, and I have a calibration stick here that allows me to calibrate the video. And when I hit play, you can see that I placed a point in the center of the ball at every frame, allowing me to get the position and the exact time it was at. Here you can see the position versus time graph, and it is approximately linear, meaning the velocity is very similar and almost constant. And here you can see the plotted in a table the time and corresponding position values. Here is my glow script. As you can see in my code, my initial position is 0.00238, which is the initial position in my tracker video, and the velocity 1.34 meters per second, which you can find that I put the picture of my calculations in the second slide. Here delta t is 0.016 seconds, so the loop runs every 0.016 second, and you can see down here the velocity update formula and the position update formula are down here and allow me to calculate and update the position every time the loop runs. As you can see, continuing on right here is the velocity versus time and position versus time graph. You can see that the position versus time graph is sloping upwards with a linear line and a constant slope, meaning that the velocity, as you can see down here, is constant, meaning there is no net force and there is no acceleration. Here is the observed versus predicted graph. As you can see, the points down below, the blue is the observed from tracker and the red is from my computational model. In the beginning, the blue and the red were very similar. However, the computational model stayed linear with a constant velocity. However, the blue slowed down, meaning that there was some other force and the F net was not equal to 0. And thus it slowed down and gradually became slower and slower and had a downward sloping line. So what if we flip the axis? If we were to flip the axis, you see this graph right here, both of these lines would be downward sloping because the ball would be moving in the negative direction. Thus, the magnitude would be the same, but the directions would be flipped if we flip the axis. And was the net force of 0 justified in the computational model? So, no, I do not believe that they were, because in our observed graph, we can see that the velocity is not constant, meaning that there is some force, most likely friction or air resistance, that is going in the opposite direction of our applied force and thus slowing the ball down. Therefore, we cannot justify putting a net force of 0 in our computational model. And thus, it is very hard and difficult to determine the amount of pushes and pulls that go into making an object have 0 force, because there are so many things that go into it. However, to achieve more accurate results in this lab report, we could factor in the coefficient of friction and thus get a more accurate representation in our computational model, or we could use an object that has a very low coefficient of friction, and thus the computational model and observed values would be very similar. Thank you for listening to my lab report.